So we're going to continue the analysis of slider cranks. In this lesson, we will review velocity analysis and the derivation of the velocity analysis using the vector loop equations. If you've got some troubles or questions with the position analysis, I would encourage you to go back and review that video and look over the notes. I'd be more than happy to answer any questions, but in order to complete and understand the velocity analysis, you need to understand the position analysis first. So in velocity analysis, we take the similar kinematic diagram as we had before. So we've got R2, R3, R4, and R1. Our vector loop for this is R2 minus R3 minus R4 minus R1 equals 0. We know some things about this slider crank. We know the length of link 2. We know the length of link 3. We know the length of link 4. We know the orientation of link 1, its theta is 0. We know the orientation of link 4, its theta is 90. What we're solving for, what we need to find here is going to be d. D is going to change, and theta 3. So if we start out with this position analysis, we can solve for this position analysis. If we input to the system theta 2, then we can get out of this theta 3, 1, and theta 3, 2. There are two valid solutions. What we need to do now is take the derivative of this expression, d dt, and we take the derivative with respect to time. What we end up with is velocity of link 2, velocity of link 3, velocity of link 4, and velocity of link 1. When we do that, what we get is an x component and a y component. We take the derivative of the position vector with respect to time. We get a prime. This is actually dA dt. So this is the time rate change of a times cosine of theta 2 minus a omega 2 sine of theta 2. This is the x component. For the y component, we get a prime sine of theta 2 plus a omega 2 times cosine of theta 2. And similarly for vector 3, vector 4, and vector 1. We take the derivative of this expression. What we end up with is this expression for velocity. So here's our velocity vector loop equation. Okay. So we have x components for each vector and y components for each vector. What we'll do is collect those x components and collect the y components. And here's what we have for an expression. So just to kind of pull this out, this is vector 2, vector 3, vector 4, vector 1, vector 2, vector 3, vector 4, vector 1. Okay, so we can now apply some known conditions we have so that we can simplify these expressions. So the known conditions are the following. Theta 1 is 0 and theta 4 is 90. If you remember back to that diagram, okay, theta 4 was measured here. Okay, in this case, theta 4 does not change. It's always 90. Theta 1 is 0. Omega 1 is 0 and omega 4 is 0. So these two links are not rotating. Now what is given or input to the system is going to be A, B, C, theta 2, and omega 2. So these are knowns to the system. And we perform a position analysis first. We solve for theta 3, 1 and theta 3, 2. And then once we do that, we can solve for d prime and omega 3. Okay? So plugging those knowns into the expression for x and y, we can simplify this first one. So a does not change with respect to time, so that goes to 0. B does not change with respect to time, that's 0. C does not change with respect to time, that goes to 0. Omega 4 is 0. And omega 1 is 0. So these all go to 0. Okay. Nextly, again, A prime, 0. B prime, 0. C prime, 0. omega 4, 0, and in this case d prime. Okay, d prime changes, but sine of 0 is 0, so this goes out. Okay. All right. So we've got these expressions. When we apply these known conditions, we end up with these two expressions that are simplified. These two expressions can be solved simultaneously. So I just want to kind of pick apart these two expressions and solve them simultaneously. I will circle in blue the known values. A is known, W2 is known, omega theta 2 is known, B is known, theta 3 from a velocity analysis perspective is known. It comes from the position analysis. Now, again, there's two solutions here. Okay, A is known, omega 2 is known, theta 2 is input to the system, B is known, theta 3 comes from the position analysis. And similar to this, there are two solutions. So I can solve these two equations simultaneously, and I end up with these two expressions. So this is important. Magenta is important. These are important. This is the expression for d prime. So this is d dt. So basically this is a velocity. And this is an expression for omega 3. This is the angular velocity. So these are two important expressions. What's more important is that you have to solve position first. Now, what do these two expressions mean? Well, we've got d down here. Basically what we said, we've got d prime, or d dt. Okay? So that is actually the speed at which this length is growing. Okay? Conveniently, not conveniently, actually the way we set it up is B moves parallel that. So it turns out you know that this is actually d prime as well. So this is the speed at which the piston is moving away given a known position and known input angular velocity. The other expression we know is going to be what is the angular velocity of that link 3. So there you have it. You've got the vector loop for velocity of a slider crank. We've derived it in this case for an offset slider crank, right? So, but if C were 0, it would be an inline slider crank. You can go and analyze, for example, the velocity of the piston in your car at 3,000 RPMs. You could do it for a full circle, full rotation of the crank. But you have the expressions that you can create a MATLAB function. You can solve by hand. You can put in Excel. But you have the expressions to basically analyze the velocity of a slider crank. If you have any questions, please don't hesitate to ask them. Post them on the Blackboard discussion forums. Ask a classmate. Email me.